Second session on planning, heuristics, and search. Our first speaker is Ron Alford on the feasibility of planning graph style heuristics for HTN planning. Thank you, Ron.
Hello. So the first thing, HTN planning, is the problem of decomposing an initial task that we want to accomplish into a sequence of executable steps. So there's lots of examples of HTN planning, but some for here are encoding control knowledge for planning, such as agent planning in robotics and simulation, from R2 to Johnny, a personal assistant, planning and mission generation for games, commercially in Killzone 2 and in papers for like Elder Scrolls and Armed Assaults, many, many more. Also representing and planning with processes and hierarchies outside the normal classical realm, with such as composing web services from Evan Sirin et al. And many more recently, program configuration from Soltani. And in general, it's more expressive than classical planning, even to the point of being able to express undecidable problems. So the question for this talk is, how does this expressivity affect what HTN heuristics can and cannot exist? So this is a little bit redundant for this crowd, but sorry. Domain-independent heuristics in search. Why do we want them? So, our problem spaces, even in HTN planning, are intractably large to search. So we want a heuristic, which is technically underestimates the distance to the nearest solution, or at least we like to pretend it does. And it's usually based on solving a relaxed ground or propositional version of our original problem, where we relax the semantics of what it means to be a solution, make it easier to find a solution. This relaxation should take low-order polynomial time, because we need to be doing it very quickly, many times. And a solution to the full problem needs to imply a solution to the relaxed problem. So this is a little bit of safety constraint, but not necessarily vice versa. And there is currently, I was going to say that there is currently only one state-independent HTN heuristic, but I talked to Pascal, and he has a second one coming in SOX. So if you're interested in this topic, he has a new, much improved heuristic coming up shortly. So, more detail on HTN planning, since this is a theory talk, sorry. The purpose of HTN planning is to complete a task, where a task is either primitive, corresponding to something we know how to execute directly, such as walking between the rooms or drinking coffee, and it's non-primitive it's called non-primitive when it's an abstract task, because it's traveling between here and LA. This can be done many different ways. And we need to recursively decompose non-primitive tasks until we get a primitive task we know how to execute directly. We use methods, which are recipes on how to accomplish abstract tasks, to decompose these. So for traveling from home to LA, we might start off and then decompose it into buying a ticket, traveling to the airport, flying between airports, and traveling from the last airport to LA. And notice this is recursive. So we have to decompose the other two travel tasks. And you can go on ad infinitum there. So formally, every HTN problem consists of an initial state. This is propositional planning, propositional HTN planning, because we're talking about heuristics here. Every problem contains an initial state, which is just a collection of propositions. Actions will change their state, and they will have a name, which corresponds to the primitive task, a precondition, which is just a logical formula over the state that needs to hold for a condition to be executed, and an effect on the state, which is just a set of propositions to add or delete. Most of you should be very familiar with this. A task network is a labeled directed acyclic graph of tasks to accomplish, where edges represent ordering constraints between the tasks. Nodes are labeled with tasks in the graph, which are either primitive, these are with action names such as drink coffee and write, or they're non-primitive tasks, such as work. And we have a set M of methods to decompose a task, where a method is just a pair between a non-primitive task name and a task network. So here's a method for working, where we drink some coffee, write on our paper, and do some more work. So it's a recursive decomposition. We decompose a task network by replacing a node in the network with a corresponding methods network. So here we start off with work, and we replace it by its method to get drink, write, and work. And we replace it again to get drink, write, and then work some more. So we will never finish our work. Primitive task networks. So if all the names in a task network are primitive, we call that task network primitive. and the whole point of HTN planning, or the decision problem, is to find a primitive network where there is an executable total order over that network. So some differences between HTN planning and classical planning, just to orient some of you in the crowd. So a classical planning problem is a set of operators. This is propositional. So initial state and a set of goal states, or a description of a set of states. There are no methods and no initial task network, and the objective is to find any executable sequence that takes us to a goal state, without restriction of an executability on what actions we can insert. So what strips, classical planning, one of the most common heuristic, basics for the heuristics is a decision problem based on planning with positive preconditions and only positive effects and a positive goal. We denotate this by strips with positive effects and positive preconditions. This is most famously instantiated in with FX relaxed graph plan. It's polynomial time to find a plan. You just apply operators until you reach a fixed point state and test to see if your goal holds. But it's NP hard to find an optimal plan. And this is the basic for many influential classical planning heuristics. There's another class of problems which isn't used very often, which is strips with just positive effects. So here, our operators have positive effects. There's arbitrary preconditions, arbitrary goal, and it's NP complete to find a plan, and the same for optimality. So what are our corresponding classes for HTN planning? Are HTN planning with positive preconditions and effects, HTN planning with positive effects, and the decidability of these and the complexity of these were previously unknown. So that's what we're going to be talking about in this paper. But if either of these, we could do either of these in polynomial time, we'd have the basis real quick now for a heuristic for HTN planning. But no. So almost all delete-free HTN planning is NP hard, even in the case where the actions have at most one positive precondition and one positive effect. Methods are acyclic, they're regular, meaning they only contained one non-primitive task, and they are totally ordered. This is by itself, even before the delete relaxation, this is in NP. And why is this? This is because we can encode an NP-complete problem into a delete-free HTN planning problem. So in specific, CNF SAT. And before you all get lost trying to find a solution, I've posted one there for you. So for each variable in our formula, we're going to have two propositions representing whether that formula is going to be true or going to be false. We'll have two methods corresponding to setting one of those variables, and then going on to set the next variable. So in the method choice, we'll determine which of those two propositions is set at the end of our task. So this will just step through. An example run through here is setting not v sub 1, or the proposition corresponding to it, setting v sub 2, setting not v of 3, and setting v sub 4. So this would be a satisfying assignment to ours. Then we need to check the disjunctive clauses. So for each here, very similar here, is that for each disjunctive clause, we have methods to test whether at least one term is true. So checking, here we have methods to check for whether V1, for the first clause of checking whether V1 is true, not V3 is true, or V sub 4 is true. And it turns out the assignment we picked on the last page will let us step through this clause and find a primitive task network which is executable. So, and because we've now encoded CNF SAT as a HTN planning problem, we know that HTN planning is NP hard. But now we want to, so this is nice, or actually, well, it's kind of bad in some sense, but we're going to go a little bit further today. We're going to show that every solvable delete-free HTN planning problem has a polynomial-size witness. So this will put it in NP complete. Let's make HTN planning with positive effects NP complete. So back to our original example. So this tree of choices right here is really is not a task network. So we've graphically described the process of HTN planning. But this is really a history of decompositions which forms a tree where the leaves are the current task network. So if this task network, if the leaves of this tree are executable, then this tree is a proof that their original problem was solvable. And this is not me, this is Geyer and Bircher. But in the general case. But we can't use this directly to prove that HTN planning is N and P, because this may be exponential in size, and we need a polynomial-size witness that can check in polynomial time to prove that it's N and P. So for every problem that's solvable, we need a polynomial-size witness. So say we're given a witness, or we're given a solution to an HTN planning problem. So we know this is a full decomposition tree, and it may be exponential in size. But we know in delete-free planning we can only add propositions to the state. So we can prune the tree, right here, to the minimal tree that contains those actions. So we cut off the rest of it. We can use a pumping lemma, and using the original solution, we can construct a table. I'm going to skip the details of that today. We can construct a table to show that this tree still has an executable expansion. You can use a pumping lemma then to shorten the tree to polynomial height. And so we have a polynomial height, polynomial width tree with a polynomial size table that proves it's executable. And that shows our decision problem of HTN planning with positive effects is N and P. So we know that our target class of HTN planning is NP complete. So it has a polynomial size witness, but it can also encode SAT, so it's NP complete. So just ignoring the deletes and the negative preconditions in our problem is not enough to create an HTN heuristic. We're going to have to further relax the semantics in order to find a polynomial time decision problem. And this is one candidate here, which is task insertion HTN planning. So this is also from Geyer and Bircher's 2011 paper, which I based most of my thesis off of. Thank you. Task insertion HTN planning allows the insertion of arbitrary operators into the task network. If you relax it to, if you restrict it to the case of TI HTN planning with positive preconditions and positive effects, it ends up being a polynomial time decision problem. So we just insert, same with FF, relaxed graph family, we just insert operators to reach a fixed point. Instead of testing for a goal, we test to see if there's a parse of the HTN tree in the final state, which is similar to testing if a context-free grammar is empty. So given that this is polynomial time, that means that task insertion HTN planning with positive preconditions and effects is a candidate for an HTN heuristic. A consequence of this is that we can't reduce SAT to TI HTN planning, so it's useful to go step through of why this can't be anymore. What happens to our original encoding? It's good that it fails, by the way, because otherwise we wouldn't be in polynomial time. So we go through and we start executing our choice over which variables to set. But now the planner can insert arbitrary actions to set the other propositions that weren't in our task network. So it can go and set V2, or not V2, it can go set, and by the end, it could have set all the propositions, even though our task network only stepped through some of those. And this would allow nonsensical traversals through our set of clauses of requiring a variable to be true and false. So it's fine for the task insertion semantics, but it doesn't map back to our original CNF SAT problem. So the conclusion today is that delete-free planning HTN planning is NP complete. So this will also apply to animal, so at least the hardness. Heuristics based on delete-free HTNs must further relax the semantics. And TI HTN planning is just, with positive preconditions and effects, is just one candidate. In fact, there may be many. And so that's kind of what's exciting about this, what I find exciting about this result. And so we need to explore the trade-offs between the complexity of our decision problem here. It has to be in polynomial time, but there's different orders there. And the fidelity of how well it maps to HTN planning, their original problem. So to try to minimize our loss in the semantics. So thank you.
So, thank you for the talk. Are there any questions? Yes.
So you said it was exciting that there could be many. Have you started exploring any yet, or is that still sort of future work?
Yes, I have 2 candidates. But
And they are?
well, that's a dangerous question. One is that both involve restricting the set of candidates to a feasible set of insertions. So real quick now, one way to do it is I have a translation of HTN Planning to classical. So you could use that translation to classical planning. When you delete relax, it actually comes complete regardless of the method structure. And you could use the run in relax graph plan to generate your set of actions that you then test for a parse of the tree on. So that's one. It's a little bit hard to tell what the semantics of that are. So I'm working on ones with more formal semantics where you can actually say something about the heuristic beyond, hey, it works.
So the problems you're solving right now, do you have, presumably the performance of HTN planning systems is really quite good. Do you have insights into whether you're working with tractable fragments of what's otherwise an NP-complete language?
I think I missed the question.
So, so the problems you're solving in practice with these systems, are they polynomial, or are they theoretically NP-complete, but the performance seems to be quite good? Or?
Oh, you mean theoretical for the, so what fragments of HTN planning we're working with?
Sure.
Okay, in general, most HTN problems end up being something called totally ordered tail recursive, because they're trying to solve classical problems. And this class of HTN problems has the same expressivity as classical planning, so there's no mismatch there. There are some ones for like the Sultani one is using an acyclic decomposition with partial orders between things. That I'm working on trying to prove is in X time, so it's actually more expressive than propositional classical planning, and so that's a case where it's more difficult, and so that's we actually do need the heuristics there to search to make it tractable, because at least to find good solutions finding good solutions that are tractable.
Any more questions? Okay, well, let's thank the speaker again. Thank you.